Okay, we are resuming from break day 4. I'm going to draw a chart here. Maybe I'm going to do it wrong. Null hypothesis is true, and we reject. So the outcome of the test, in terms of whether or not it is correct, often you don't learn whether it's correct until later. But at least in theory, your null hypothesis is either true or it's false. And you can be, this is not the result of the test, this is truth that you don't know, but you know, mu is more or less 160 centimeters. And that's actually true, but the test may reject that. That's a mistake. That's an error. This is what we call type 1. Type 1 error. We reject the null hypothesis even though it is true. So here's our distribution under the null hypothesis. We have a test statistic value that is more extreme than our critical point, which came from alpha. It's more extreme, or down here. And so we have an unusual sample, but a sample that is unlikely to come from this distribution, but it can happen with probability alpha, that we make a mistake and the test result is wrong. The test rejects the null hypothesis. It says that this value is too extreme. It is extremely unlikely that this value came from this distribution, from the null hypothesized distribution. So we reject it, but in fact, that's the wrong thing to do. It's simply a rare but possible sample. We had bad luck. And if the null hypothesis is in fact true, and we perform the test, and we have a modest test statistic, we say, here's the distribution under the null hypothesis. Here's what we got in our sample. It looks modest. It's not extremely high or extremely low. And so we accept our null hypothesis, and that's good. The test has the correct result. Correct. And it's possible that the null hypothesis is not true. In fact, actually, we won't know. The null hypothesis is wrong. It is false. Our test could have this value, although this distribution is not correct. So, this is the distribution under the null hypothesis. If we accept the null hypothesis, we have a sample that is reasonable for this distribution. But this distribution might be wrong. This is what we assume in the null hypothesis, and it might be wrong. And so this is an error. If the null hypothesis, this whole distribution, the position of it, this is wrong. But we accept it as being correct. So this is error type 2. False positive, false negative, sensitivity, specificity are other words for type 1 and type 2. And the null hypothesis is false, and we rejected it. We said, we think it is false. We had an extreme test statistic. We said, this statistic is not likely to come from this distribution. So we reject this distribution, this location of the distribution, because this thing is extreme. It is not likely to occur in a sample if the null hypothesis is true, and it is sufficiently extreme or unlikely that the p-value, that area, the negative, this area, for this test statistic value, this is the p-value for the test, and this probability of being this extreme or more so, as at least at this extreme, here or more. The probability of that is less than alpha, this probability, two-sided test. We take both sides. The probability is the p-value. So that area is less than the alpha specified area. Therefore, we reject the null hypothesis. And that was the right thing to do. The null hypothesis is false. If the null hypothesis is false, it is correct to reject it. This type of this is important to consider the probability of making either type of error. The probability of a type 1 error, that is, when we reject a true null hypothesis. The null hypothesis is true, but we decide to reject it. That's an error. This is the probability that is specified in alpha. So, in the hypothesis test procedure, alpha is specified a priori, and it is defining the probability of making this type of error in the decision-making process. How do I get... this is the other type of error is maybe less dangerous, or it's when you don't have sufficient statistical information to reject what should be when you should reject it. So you fail to accomplish a reject result. And this is, let's see, I need to, this relates to the power of a statistical test, which is the ability for the test to detect a situation of a false null hypothesis. It is the ability, the power to be able to correctly reject when, let's see, this is difficult without, I need to get into a specific alternative hypothesis and draw really messy graphs to show the power. So I should wait, I think, to do that. But sample size is what buys statistical power. And I can draw a little bit a picture to show how, all else being equal, if you have a false null hypothesis, if it's wrong, a larger sample size has more statistical power, is more likely to reject it, to detect a difference, to detect an incorrect null hypothesis. And I'm going to try the blue pen.
I have last one right here.
But I need a different,
Okay.
I want a different color, and
Okay.
hopefully it will be visible, but maybe I can do this. So here's our null hypothesis distribution. This is what the distribution of the test statistic this thing we calculate from our sample. This is the distribution of it if the null hypothesis is true. Now maybe the null hypothesis is false. So blue is false null hypothesis. Now we're talking about, there are many ways the null hypothesis could be wrong. But normally we are talking about the null hypothesis being wrong in terms of the mean value that it states. So maybe we have something like, what was our standard deviation? 12. 160. Well, it's all standardized, so 3, 6, 9. Okay, about here. So here's another possibility. Here's another distribution. And this is a possibility to say the null hypothesis is wrong. This is not the mean. Instead, the mean is higher. The blue is the correct thing. You have to get into some terminology with specific alternative hypothesis that gets messy. But just think of the picture. Is that maybe this relates to a mean in the population, not 160, but 169. If maybe. I think that's right. Okay. So this is what's true. And you can imagine this situation, a specific situation where the null hypothesis is false. And so the blue is our actual reality thing, and we get some test statistic that is just a second. Oh Christ, I knew I'd screw it up. So here's this guy, and just a second, and this comes down. There's Here's our critical value, okay, here, and compared to here. Okay, so we have a test statistic giving a accept the null hypothesis result. We assume the null hypothesis, we look at the statistic value, this thing. It seems reasonable, so we accept the null hypothesis, and we have made a mistake. Because in truth, the distribution is centered up here at 160. The mean height in the population is higher than the value of the null hypothesis statement. So this is the truth, but we got a sample that's consistent with our null hypothesis, and so we accept the null hypothesis and we are wrong. And we can have a sample that is more extreme compared to the null hypothesis. It's beyond our Z alpha value, our critical value that comes from alpha. It's higher. So we reject this null hypothesis. And we just say, that just means it's wrong. And we can make a confidence interval for the mean, but we have a test statistic value here. It will say that we're wrong, that the null hypothesis is wrong, and that's the right answer because we're saying that the blue thing is the truth. So rejecting is the correct thing to do, and that can happen. Okay, so now this thing here, this is going to be tough, but anyway, this is our measure of standard deviation, or the standard error in the sample. This is how spread out it is, the numbers in the sample. And this is the sample size, the square root of n, and together this quantity, s over square root of n, it's good to know, this is often called the SEM, or SEX bar. The standard error of the mean, or the standard error, and then saying x bar, and this is what we're dividing. How do I do this? This is where the transform is a problem. But if our sample, let's say, okay, we have a certain sample mean, and we have a fixed, a certain spread, variance in the sample. If those remain the same, but the sample size increases. Let's say the sample size goes from 16 to 64. When we did this, we used square root of 16, so 12 divided by 4, we had a 3 here. We divide that, and basically we have a 3-unit spread here. So 3, yeah, anyway. If our sample size, square root of 16 is 4, square root of 64 is 8. If we instead had a sample size of 64, the algebra of it, maybe not satisfying, but mathematical fact, we have the 12, instead of 12 divided by 4, we have 12 divided by 8. So our standard error of the mean would be 3 in the small sample size. In the doubling on the square sample size, we go down to 1.5. So, now I redraw the pictures. We have a fixed difference. Everything else is the same. The only thing that's different is we have a larger sample size. We have some difference here, but this thing is not 3 units fat in standard error. It's get rid of this. It's 1.5. It's half as fat. So 1. So now it's a lot more. It's a lot higher. Comes down. There's 1 standard deviation, 2 standard deviations, 3 standard deviations, and now it's down to almost 0. And the same thing with this one. With the blue, it would be much tighter. So now we have 1, 2, let's see, 1, 2, this is for 0.05. This, instead of our critical value being out here, the whole thing is narrower. So to get our alpha probability of making a type 1 error, we go to a critical value that's here. And so any sample that's more extreme than that will have a p-value, will have area under the curve, probability, that is smaller than alpha, and we will reject our null hypothesis. So this sample, we were comparing two. One was accepting and one was rejecting the null hypothesis. I didn't move those. But now, the one that was accepting the null hypothesis in error is now above the critical mark because the distribution got tight. And so this sample with this sample size, we were wrong with this sample. We were type 2 error. But by increasing the sample size, we moved this critical value from here into here, half as wide, and now our test will reject this null hypothesis in favor of some alternative. It will reject the null hypothesis. And the power of a statistical test, power equals 1 minus beta anyway, the power under a specific alternative hypothesis. The power of the test is, beta is the probability of the type 2 error. That's what I need to, this is the beta. 1 minus the power. The probability of making this error is beta, and this error happens, we have a specific alternative hypothesis that is correct, but we don't recognize it. We accept our null hypothesis in error. We're wrong about that. And to talk about the power, or the 1 minus, the probability of type 2 error, you have to consider it under a specific alternative. Pick something. If the mean, the true mean, is 169, will the test reject the null hypothesis correctly, or will it result in an error? And we can get the probability of this error as, this is a mess. We fail, we accept the null hypothesis. This is our error. This happens if we do not have an extreme statistic. We have a moderate, believable value. Something here, or here. In the reasonable under the null hypothesis. I don't care which sentence. Reasonable value. So, if we have a sample that is reasonable under the null hypothesis, we will accept the null hypothesis. And under this specific alternative hypothesis, the probability of this kind of sample is this. It is the area, if this is correct, right, a specific alternative hypothesis, this specific alternative hypothesis will be accepted, the test will have type 2 error if the test statistic looks reasonable under the null hypothesis. It looks reasonable under the null hypothesis if it's close to this 160, if our sample mean is similar to our hypothesized mean, if it comes in around here. And the probability of these numbers occurring in our sample according to this specific alternative hypothesis. We have to say, this is true. If this is true, what is the probability of getting something that accepts the null? And it's the area right under here. And outside of that, we have, let's see, this specific alternative, and it's much more likely that we're, right, the blue, this is our specific alternative. This is the probability of all the statistic test values of the sample. This is the probability of our sample being rejected as extreme under the null hypothesis. This is the power, and this is beta, the probability of a type 2 error, and this is the power. Under this specific alternative, the test, this picture, shows a test that has very high power to detect an invalid null hypothesis, because these things are tight and don't overlap. If we have a small sample size compared to this, if our sample size is much smaller, all else is equal, but the sample size is smaller. That's smaller, this number is, this standard error of the mean is larger, that's the spread, and it looks like this. And now we have a situation where these things overlap a lot. It's more difficult to detect the separation. There is more overlap in these distributions. So for this separation to be detected, we need to adjust the sample size to have sufficient power to detect this. And so we buy more samples, and we are buying more and more separation in these distributions, and we're buying higher power, higher probability of detecting an incorrect null hypothesis. Obviously, we were talking about a specific alternative. If we're talking about a specific alternative, which is here, we're going to need a lot of samples to be able to detect a difference. Because if we had two distributions, under the null hypothesis, it's like this, and under the alternative hypothesis, it's like that, and you would need 1,000 samples to be able to have a high probability of concluding a rejection of the null. This is a lot of mess to get. If you think you understand it, you probably don't. But this is something that takes a couple weeks to sink into your brain, or more. But let's see. I have an example. I'll maybe tell it's a good story. This whole thing, all of this, has a analogous, equivalent side in confidence intervals instead of statistical hypothesis test. I mean, fundamentally, they're equivalent tools, but with a very different expression in the end. But you can think of it in making confidence intervals for a population mean. You have all the same ideas happening. And so, let's see. If I have this sample mean and this size and the same, if I have this mean, this standard deviation, standard error in my sample, I can compute a 95% confidence interval for the population mean mu, the parameter, I'm going to get rid of this. 95% confidence interval, or whatever the hell, for a confidence interval to mirror the statistical hypothesis test in result, this number, the confidence level, it's actually the coverage probability. Anyway, this is 1 minus alpha. I wrote 95% because that's alpha of 0.05 is 1 minus 0.95. So we make sure we match the alpha, we match our confidence coverage probability, our confidence level with alpha, and we will match results with the hypothesis test. Okay, so this thing is x bar plus or minus there was that critical mark that on my curve. There was this thing that I called Z critical, where we reject out here and we accept in here. That's this. It's 2, more or less. This is about 2. That's meaning 2 standard deviations for a 95% confidence interval. And the standard error times the SE standard error of the mean. That's, which is that thing. I will put numbers now. This is our sample. What the hell did I say? Doesn't, whatever. 180. X bar 180. S 12. Sample size 16. Put the numbers. So 180 plus or minus 2 times, actually it's like 1.95. S over the square root of n is 3. 180 plus or minus 2 standard error of the mean. So, we have we have X bar at 180 and our confidence interval, our 95% confidence interval, which that's determined by this thing, which is tied to the alpha level. For 95% confidence interval, it's about 2. And 180 minus 6, so 174, and up here to 186, this is a 95% confidence interval. 174 to 186 is a 95% confidence interval for the population mean. Our hypothesis test, our null hypothesis was that mu equals 160. Our confidence interval is nowhere near this null hypothesis. If you remember, these numbers, we had a p-value of tiny p-value. When I use these numbers and computed a p-value for the hypothesis test with a null hypothesis, saying the mean, the population mean is 160, I rejected the null hypothesis with extraordinarily strong statistical evidence. The sample was extremely unlikely to come from a distribution with this mean. Similarly, consistent, it is consistent that we compute a 95% confidence interval for the mean, and it does not contain the null hypothesis. This is equivalent this confidence interval does not include let's see, how do I say it? If you start with the confidence interval, you can say that every hypothesis test, every null hypothesis outside of this interval, if you do the math, you will reject any null hypothesis value that's here, here, here. We had it at 160, but if we were at 170, we would reject the null hypothesis. If we were at an alpha equals 0.05 significance level. So that's the mirror side of it. You can look at the confidence interval and figure out which hypothesis test, what the hypothesis test would give as an answer, looking at the confidence interval, or you can do it the other way around. I mean, they're equivalent, just a very different way of expressing the fact that, this population it is not likely that we get this sample with this kind of confidence interval coming from a population with a mean over here. Because if we have this confidence interval, let's see, this range, this interval, represents a range that there is the probability that the confidence interval overlaps, includes the mean, is 95%. There is a 95% chance that our sample constructs a confidence interval, and that this interval will include the true mean. if we want to be much more confident than 95%, if we want to go to a 99.99% confidence interval, we have to have an interval that we are very sure will include the mean. If we want to be that sure, it's going to get big. So the confidence interval trade-off is precision and probability. If you want high confidence, you cannot be precise. If you want high precision, you can't do it with high confidence unless you have a lot of money and you can change your sample size. And that sample size, where was my little thing? This was 180 plus or minus 2 times S12 divided by square root of n, either 4, or if I go to 60, from 16 to 64, this goes from 3, 12 divided by 4, to 1.5, 12 divided by 8. So I go from plus or minus 1.5. And then, so I was here, and with much higher sample size, I can be much more precise about my range. My confidence interval is half the size that it was before. It's much more precise, twice as precise, for the same confidence level. So I bought more samples and I increased my precision with the same confidence. Or I could hold the same precision, I could increase my sample size, and I would be buying higher confidence. It's just the balance. So your statistics book probably says that you can't do hypothesis test for a null hypothesis of a difference. You can't test, let's see, how do you say that? The statistics books, other than biostatistics, will perhaps say that you can test equivalence or equal to. The mean equals something, or the difference is 0, and test to reject it. So you have the potential to reject an equivalence, or as a result. The result is the rejection of the equivalence. You can also instead of detecting differences, so that's where you assume it's equivalent and you look for a difference. You can do it the other way too. It's the inversion of two one-sided tests principle. It's messy. It's called equivalence testing. And it comes up in, well, if you want to demonstrate, you have a null hypothesis of some difference and you wish to reject that and demonstrate that it's equal. It's just a hypothesis tested, just kind of flipped inside out, but it works almost the same, and it comes down to, you can do it with a confidence interval. You construct a confidence interval for the, you have your sample mean plus or minus 2 times the standard error of the mean, and you have some confidence interval, and if it's close to, this represents the difference in two things, and if that confidence interval contains 0 and is not too fat, you say, ah, good. I can conclude 0 difference. Or if it's the ratio of two things, because you do log transforms, and so all your addition becomes multiplication and subtraction is division, and you do ratios and stuff. It's a common logarithmic transform of data is a common method to make things work. And in that case, you end up with, saying, a confidence interval of, in the specification